Hi, my name is Ignas. I was quite interested in energy as a solution to most humanity problems from a young age. First, my interest was focused on renewable energy, and then, once I learned about fusion, I have seen it as an ultimate energy source. Since then, I have joined the board of directors in Focus Fusion Society. I served as a secretary and helped raise money for fusion energy research. I think that energy is the basis of the progress our society has made, and making it much cheaper and more available would benefit everyone. This is the promise of focus fusion energy.
Hi, I'm Warwick. I'm a specialist in designing and building numerical simulations. I first got interested in fusion energy when I was finishing my PhD, and I read a little book called Voyage Through the Plasma Universe by Hans Wilhelmsen. I've been building a simulation of a plasma filament for LPP fusion that is a small company trying to produce cheap, clean, abundant energy with a reactor that makes use of the naturally turbulent properties of a plasma rather than trying to eliminate them.
We at LPP Fusion are developing the focus fusion technology. It's a new source of energy that will be clean, safe, unlimited, and far cheaper than any source of energy existing today. It's based on fusion energy, the same source of energy that powers the sun and the stars. What happens is a series of instabilities driven by the pinch effect, each one of which makes the plasma denser and hotter. So the first one, which is illustrated in this animation, is the filamentation instability. So you start out with a smooth plasma, and the plasma comes together with what are called filaments, which are dense vortices of current pulled together. So that makes the plasma, that's the first step in making it hotter and denser.
The simulation is of one of these filaments, as shown here, that initially goes from the anode to a tooth that acts as a lightning rod on the cathode base plate, and then over time it will move out under its own J cross B force and then move along the cathode rod as shown there. So basically, so far this simulation's been through several redesigns already up to this point, and in its present incarnation it's reached 240 nanoseconds of simulation time, and our goal is now to get it to 350 nanoseconds, which will demonstrate some more interesting phenomena in the simulation. Now this is a 2D simulation of a cross-sectional plane through the plasma filament, extending out past the cathode rod, which is represented by this hole in the graph, and this side of the graph goes against the insulator that is around the anode. Now this is a fluid simulation, which means that we describe the plasma with a density, a velocity vector, and an isotropic temperature for each fluid. And we have three fluids for simplicity. We have the neutral gas, singly ionized positive ions, and the electrons. Here we have the current profile, the inductive field, the applied electric field, and the magnetic field. We evolved the current and the inductive field together according to Maxwell's laws and fluid acceleration, and we set the applied electric field in order to call forth the total current that we want at any given time, but the shape of the current is set according to resistivity in different places. As heat increases because of resistance, we get the scope for ionizing collisions, and so ionization fraction grows. Now where does the magnetic field live? it lives between the tooth and the insulator, basically, because this is where there's constructive interference between the clockwise field about the filament and the anti-clockwise field about the anode. Now this means that we get the J cross B force, which applies in the same region, and we also have ionized density appearing there, so those things together mean that we have this outward force affecting the ionized plasma, which then drags everything with it, and that's what this blue is representing, that's becoming greater than the velocity we got from thermal pressure initially. This means we're going to get a wavefront because energy and material is being propelled outwards away from the insulator. It leaves a very low density region in its wake, and fully ionized material is being pushed outwards into partially ionized material, and we'll get a front of ionization. Viscosity and heat conduction can transfer energy forward out of the wavefront, so the simulation has to quantify the extent of that. Finally, we're expecting that when the wavefront crashes through the partially ionized region, it will roil back on itself in a Rayleigh-Taylor instability.
We have recently integrated a new peer-to-peer fundraising platform into our Focus Fusion website called Flipkos. To use Flipkos, you press the Become an Advocate button. There, you can enter details to create your own advocacy campaign and raise funds, either individually or as a part of a team. This way you can tell your story and help your network contribute towards fusion energy research.
The simulation that Dr. Dumas is developing can help us reach our goal faster. The Focus Fusion Society is funding grants that partially fund the simulation work, just as they've funded grants that help us with our experimental work. If you want to help fund this effort and get us to fusion faster, then press the donate button. If you want to spread the word, press the button that says Become an Advocate. And thank you.